All right, welcome everyone. Today we're going to jump right in and tackle problem 1.26 from the legendary Irodov collection. Now, if you studied physics, you know this book is famous for its really challenging but also really insightful problems. So let's break this one down together. Okay, so here's the deal. We're told a particle is moving around, and its position is given by these two equations. One tells us where it is on the x-axis at any time t, and the other tells us its position on the y-axis. Our job is to figure out what these formulas are really telling us about how this particle is moving. So here's our game plan. First, we're going to make sure we understand exactly what the problem is asking for. Then we'll do a bit of detective work on the particle's path. This is a crucial step. After that, we'll dive into the nitty-gritty of part A and part B. And finally, we'll tie all the math together to see the beautiful physics behind it all. First things first, let's really unpack this challenge. With Irodov problems, you've got to be super precise. So let's get crystal clear on what we actually need to find. The problem's really asking us for two things. For part A, we need to figure out the total distance this thing actually travels in a certain amount of time tau. And for part B, we need to find the angle between its velocity and its acceleration. This second part is really cool because it tells us a lot about the fundamental nature of the motion itself. Okay, now hold on. The temptation here is to just, start crunching numbers and differentiating everything right away. But wait a second. With problems like these, taking a step back can be a real game changer. What if we could figure out the actual shape of the path this particle makes? That could give us a massive clue, right? So let's put on our detective hats and see if we can decode this path. The trick, you'll see, is to try and get rid of the time variable. If we can find a direct relationship between just x and y, we'll have the geometric shape of the trajectory. Here's the strategy. We're going to take our x and y equations and just rearrange them a little bit to get the sine and cosine terms all by themselves. Then, and this is the key, we use that one trig identity everybody remembers. Sine squared plus cosine squared equals 1. We just plug our expressions in, and boom, we get an equation that connects x and y directly. No t in sight. And would you look at that? The result we get is x squared plus y minus a squared equals a squared. I mean, that should be ringing some serious bells. It's the perfect standard issue equation for a circle. This right here is the big aha moment. The particle isn't just wandering around on some weird, complicated curve. Nope. It's just tracing a perfect circle with a radius of a, and its center is at the point 0, a. And knowing this, it changes everything about how we're going to solve the rest of this problem. Okay, so now that we know we're dealing with a circle, let's roll up our sleeves and tackle part A, figuring out the total distance the particle travels. So how do you find the distance something travels along a curvy path? Well, you basically have to add up all the teeny tiny steps it takes. And in the world of calculus, that just means we need to integrate its speed over time. So first things first, we need to find its velocity so we can get its speed. Getting the velocity is pretty straightforward, actually. We just differentiate our x and y position equations with respect to time. That gives us the two components of our velocity vector. The speed, well, that's just the magnitude, the length of that vector. We use a little Pythagoras for that, and look what happens. All that sine and cosine stuff, it just simplifies away. And this result is a huge deal. The speed is just a times omega. But wait a minute. A and omega are both constants. That means the speed is constant. And what do you call motion in a circle at a constant speed? That's right, uniform circular motion. Our math just confirmed the physical insight we had earlier. It all fits. Okay, so since the speed is just a constant number, that big, scary-looking integral for distance just became super, super easy. All we have to do is integrate the constant a omega from time 0 up to our finish line, which is tau.
And there it is, our answer for part A. The distance s is just a omega tau. It's basically just speed times time. It's so simple, and it makes perfect physical sense. I love it when that happens.
Okay, on to part B. We need to find the angle between the velocity and the acceleration vectors. And this is more than just a geometry puzzle, right? The answer here is going to tell us a lot about how the particle's motion is changing moment to moment. So here's a little pro tip. Anytime a physics problem asks you to find the angle between two vectors, your brain should immediately scream, dot product. Seriously, the dot product formula is practically made for this kind of thing. It directly links the vectors to the angle between them. We've already got the velocity, so now we just need to find the acceleration. And getting the acceleration is no problem. We just differentiate the velocity components one more time with respect to time. So here they are, all laid out side by side, ready for us to do our dot product calculation. Okay, let's do the math. Remember, the dot product is just multiplying the x components, multiplying the y components, and then adding them together. And when we do that, look at this. We get two terms that are exactly the same, but one is positive and one is negative. So they just, poof, they cancel each other out completely. The dot product is 0. Now, since the particle is actually moving, its velocity and acceleration aren't 0. So the only way for their dot product to be 0 is if the cosine of the angle between them is 0. And that only happens at one angle, 90 degrees. So we've got our two answers. The distance is a omega t, and the angle is a perfect 90 degrees. But let's take a step back from the numbers for a second. What's the physics story here? What does this all really mean for our little moving particle? So here's the bottom line. We have mathematically proven 3 things. 1, the path is a circle. 2, the speed is constant. And 3, the acceleration is always perpendicular to the velocity. And when you put those 3 facts together, what do you get? You get the textbook definition of uniform circular motion. It all just clicks into place. Because the acceleration is always at 90 degrees to the velocity, it can't speed the particle up or slow it down. Its only job, its entire purpose, is to constantly tug on the velocity vector, bending the path into a perfect circle. That's your classic centripetal or center-seeking acceleration. And just to leave you with something to chew on, what would happen if the motion wasn't uniform? What if the particle was speeding up or slowing down? Well, then you'd suddenly have a new piece of the acceleration, one that points along the path of motion. And that nice, clean 90-degree angle, it'd be totally gone. It's a really cool thing to think about for next time. Thanks so much for joining me.